All right, so today we're going to talk about Lecture 5, Part 5, vectors. Vectors have a wide array of applications in engineering, sciences, and other fields. So, Lecture 5, Part 5. So we'll start off with the definition of vectors. What do we mean? A vector is a mathematical object. It's defined like this. So let me pull up the note. So a vector in the plane is a line segment with an assigned direction, as shown in this illustration. So you take a line segment in the XY plane and you give it a direction, a particular direction. And point A is the initial point, and point B is the terminal point. And the way we annotate vectors is shown here. So we can say we take this symbol to be the symbol for a particular vector. It's a letter, a lowercase letter with an arrow on top. And the alternative symbology could be to represent a vector as its initial point, concatenate it with the symbol for its terminal point, and then put an arrow above that. In older forms of literature, what they'll do is they'll use, instead of putting the arrow on top of the letter, they'll use boldface type for the symbol of a vector. So you have a wide array of symbologies for representing vectors. And this formula right here designates the magnitude of a vector, which effectively is the length of the line segment connecting initial and terminal points. This figure right here shows essentially, effectively, what is maybe considered the sum of two vectors. So vectors are additive. So for instance, if we take vector AB and we want to add to it, say, vector BC, where's vector? Oh, this is vector BC right here. Okay, if the initial point of BC is coterminal with the terminal point of vector AB, then the sum of the two vectors can be thought of as just connecting the initial point of vector AB with the terminal point of vector BC. So this would be the resultant sum of the two vectors. So we'll talk more about how to sum vectors in just a few minutes. All right. So what we can do with vectors is we can do mathematical operations on them, such as we can scale them. We can adjust their length without having to alter their orientation. So, for instance, multiplication of a vector by a scalar follows like this. All right, so if we start out with a particular vector v, some arbitrary vector with initial point p and terminal point q, all right, say we can use the one drawn in this illustration. So here's vector pq. If we were to say half, multiply vector v by a scalar 1/2, all it does is it shrinks the length of the vector by 1/2, and it retains the original orientation. Okay, so the direction in which it points is still the same as the original vector, but the length is halved. Now, if we were to say multiply the original vector v by 2, all it does is it doubles the length of the vector, but the orientation is retained. So like here would be 2v right here. Okay, and then if we were to say negate the vector, multiply the vector by -1, all you do is you take the original vector and rotate it 180 degrees so that it's now pointing 180 degrees in the other direction, and the length is still retained. And then -4/3. So for instance, this particular example, -4/3, all you do is you just take this yellow vector and multiply it by 4/3. Multiply its length by 4/3, and you retain its direction. So So negative 4/3, which would be 1 in the third. So this would be, say, for instance, negative 4/3 of b. All right. So now we have what's called the component form. Sorry, it got truncated here. Let me see if I can fix it. Yeah, there we go. The component form of a vector. And you reference this diagram on the right as I talk about the component form. Here we have another symbolic representation of a vector. Okay, it's just an ordered pair of numbers, and the delimiters of the ordered pair of numbers are these two brackets, these two angle brackets. And so A is considered the horizontal component, and B is considered the vertical component. All right, so for instance, the computation of the horizontal component. So first of all, according to the definitions note here, P is the initial point right here, and the coordinates of P are, of course, are x1, y1, and Q is the terminal point with coordinates x2, y2. So the vector V represented as an ordered pair would be the difference of the abscissas. Now, the way you do the subtraction is you start with the subtraction of the abscissas would be calculated by subtracting the terminal abscissa minus the initial abscissa. Okay? It has to be done in that order. And then the ordinates would be found by subtracting the terminal ordinate minus the initial ordinate. Okay? And so they call this value A, and then they call this value B. All right, so that's what they mean by the component form of a vector. All right. Okay, so what can we do with this? Do an example. Okay. So let's see here. So let me pull up the note. So in the example, we want to find the component form of the vector u. So here's a case where u is written in boldface notation with initial point -2,5 and terminal point 3,7. So according to the previous note, all you have to do is subtract the terminal abscissa minus the initial abscissa to get the horizontal component. So 5 becomes the horizontal component. And then you subtract the terminal ordinate minus the initial ordinate to get the vertical component. So that would be the vertical component of the vector u. So that's how u is formulated. All right. And then let's see, for part B of this question, what do we have? The vector v is 3,7, and it has an initial point of 2,4. So what is the terminal point? Okay, so here's vector v, which is 3,7. And so the terminal abscissa, which is x, minus the initial abscissa, which is 2, okay, that would have to equal to 3, the horizontal component of the resultant vector. And then the terminal point of q, which is what we're finding, minus the initial point p, okay, that would be the vertical component of the resultant vector. And so you just solve the two equations, and you'll get x equals 5, y equals 11. So the terminal point q, the coordinates of point q, would be 5, 11. All right, and so part C, what's going on with part C? Now, I apologize, the scanning, the part of the view got smeared during the scanning, but we'll see what we can attempt to work parts of this where we can. Okay, so sketch representations of the vector w, which is equal to 2, 3 with initial point 0, 0. Okay, so let's start with the first part. So if we have an initial point 0, 0, all right, so that's here in the origin. And vector w is 2, 3. So what it means is you go horizontally 2 and then vertically 3. Okay, like so. And so this would be vector w drawn as such. All right. Now, if we started at an initial point of 2, 2, which I guess would be here, all right, and then we go 2 units horizontally, and then vertically 3 units. Okay, so that would be vector W right there. And if we have an initial point of, what, -2, -1, say if that's right there, then we go horizontally 2 and vertically 3. Okay, and so this would be the answer to that third part. And then if we were to start at 1, 4, okay, 1, 4 would be here. This would be 1, 4 in the XY plane. We go horizontally 2 and up 3. Okay, and so that's how they're kind of like navigation vectors, which is exactly what these may be considered. Okay, so now we can talk about subtraction of vectors. We talked about or addition and subtraction of vectors. What the book doesn't mention, I think this is probably, when we add and subtract vectors, we use a method of parallelograms to do that, which is what the author never mentioned this, but I think back in the day it was called method of parallelograms. So let me show you how you can easily add and subtract vectors using the method of parallelograms. Okay, it's a military term, I believe. All right, so subtraction, and we'll do addition of vectors as well. So suppose we have two vectors u and v. All right, so here we have, suppose that the vectors are oriented such that the vertices, the initial points of both vectors may be considered here at some origin, 0, 0, like so. And u is specified as a1, b1. So here's vector u, all right, and its terminal point is a1, b1. Okay, and vector v, its terminal point is a2, b2. All right, so u and v are sketched thusly. Now, to add the two vectors, the process involves, well, if you wanted to add them numerically, as shown in this example right here, you essentially add the horizontal components of the two vectors, and you add the vertical components of the two vectors. And so this would be the sum specified numerically. Now, to add them graphically, we use the technique which is called the method of parallelograms. What you do is you take, so if we were going to say u plus v, all right, let's talk about the sum first. What you would do using the method of parallelograms is you take vector u and you slide it along the entire length. Just take the whole vector, the locus of points for the vector, and just slide it along vector v, retaining the direction in which it's pointing. Don't change the direction in which it's pointing, but retain the direction. And when you get at the terminal point of vector v, redraw the vector u again. So you have a second copy of the vector v. You just repositioned it here. So that now the initial point of vector u is now at a2, b2. Okay? All right, now, so what you do then to add the two vectors is you essentially connect the initial point of vector v, okay, to the terminal point of the new vector u, the vector u that you slid along vector v. Okay, so the sum then would be this right here, this vector right here. Okay, and its component form, okay, we've already calculated its component form right there. There's its component form. So that would be the resulting sum. Now, to compute the difference in component form, you just subtract the horizontal components of the two vectors and the vertical components of the two vectors. And the subtraction has to be done in order. Don't commute the subtraction. Okay, if it's u minus v, you subtract the horizontal component of u minus the horizontal component of v, and the vertical component would be the vertical component of u minus the vertical component of v. Do not commute the values. Now, to subtract the two vectors graphically, okay, so what you do is, okay, so you go back to the point, or go back to the task where you slid vector u along vector v to the terminal point of vector v, and you redrew it with the same direction and same length, and then you connect the say if we call this this vector, say u, maybe if we re-symbolize it here. I know this is going to drive students crazy if I do this, but the book was very shortcoming on this. All right, so suppose we call this u hat. Okay, I put a little hat. So the u hat is a symbol for this modified vector u right here. Now, if we were to connect the terminal point of this modified vector u hat to the terminal point of the original vector u, like so, connect them like that, okay, shown in the black vector. Then what you'll do is you'll connect the terminal point of vector v to essentially the terminal point of vector u, like so. You really didn't need to draw. What the black vector exhibits is the negation of vector v that was translated along vector u, okay, vector u hat, that is. And so what it shows is that you're effectively adding u to negative a v hat, and so the resultant vector would be found by connecting the effectively connecting the terminal point of vector v to the terminal point of vector u. Okay, but really bear in mind what you're doing is u minus v is this yellow vector is the result of effectively adding this u plus this minus v right there, and so that would be how you would manage it. So method of parallelograms, we'll probably see more of this as we go forward. Okay, it's a little bit tricky, but just if you notice through the method of parallelograms, the diagonals of this constructed parallelogram, one diagonal forms the sum of the two vectors, and the other diagonal forms the difference of the two vectors. Okay, all right. So just as a takeaway, method of parallelograms for adding and subtracting vectors. All right. Okay, so let's talk about properties of vectors. And get some more alternative representations of vectors. As you can tell, there's no consensus for vector representation. And that's because of different applications, usually coming from the military and from industry. All right, so we talked about addition and subtraction of vectors. We talked about scalar multiplication of a vector. Okay, C, of course, is a real number. And then we talk about the magnitude of the vector, which is the square root of the sum of the horizontal component squared plus the vertical component squared. Okay, and then we can talk about unit vectors. Unit vectors are vectors of length 1. So for instance, if vector W is equal to this, you can verify that it has a length of 1 by calculating its magnitude. Okay, so let's calculate its magnitude. So that would be the square root of 9/25 plus 16/25, which of course is equal to 1. Okay, so that's W is a unit vector. Now we talk about these two symbols right here. This is I and J. So I and J are both unit vectors in the coordinate plane. Okay, so for instance, if we're in the XY plane, I would be a unit vector along the x-axis. Okay, so for instance, this would be I. Okay, and then J would be a unit vector in the y direction. Okay, and that's by convention. These are definitions. So J is a unit vector in the y direction, and I is a unit vector in the x direction. All right, so properties of vectors. Well, vector addition does commute. Vector addition is associative. The zero property of vectors applies. There's the additive additive, I guess what do you call this? The u minus u is 0, and then we have the length of the vector, okay? So if we have a vector times a scalar, the magnitude of that object would be the absolute value of the scalar times the magnitude of the vector u, okay? And so vector multiplication is distributive with respect to addition. It's commutative, associative. A vector times a unit vector is the vector itself. This is actually, I think, a unit vector. A vector times a 0 vector is 0, and a scalar times a 0 vector is 0. So we'll see more of this. Okay. So what we can do is we can express a vector in terms of these base unit vectors. These base unit vectors are actually, interestingly enough, called basis vectors. So for instance, if I give you the component representation of a vector as AB, then we can take the A value out as a scalar and multiply that scalar A by the unit vector 1, 0 for the horizontal component. And the vertical component can be represented as a scalar B now times the vertical, times the unit vector in the y direction. Okay, so this would be the vertical component right here. So we'll do more of that as well. All right, so we need to, using all of this plethora of definitions, we can do some word problems to put all of this in context. So we have some more definitions before we get to a word problem. Okay, so let's do another, the trigonometric representation of vectors. Okay, excuse me. All right. Okay, yeah, so we can make use of this. Where'd it go? Copy. Is it going to paste? Sorry, technology malfunction again. I said it. All right, let me try it again. Darn it. I don't know why. I think it's just that these computers are so slow that it causes problems. Copy. All right, so we could talk about horizontal and vertical components of a vector in terms of the trigonometric function. So refer to this illustration right here. Okay. So all we do is we can let v be a vector with magnitude v, of course, and direction theta. So in this case, the vector v specified by magnitude with a direction of theta right here. And so the component form representation of a vector, of course, is a times the vector I plus b times the vector j, the unit vector j. So I and j, of course, are unit vectors. And we can replace a with its trigonometric representation. Since a is the horizontal component, it would be the magnitude of the vector v times the cosine of the direction theta. And then the vertical component of the vector would simply be the magnitude of the vector v times its vertical the vertical component would be the magnitude of the vector times the sine of theta. So we've seen this from the previous chapters, how to do this. So let's talk about a word problem. Okay, it got truncated on the left here, so I'll pull up another illustration of the word problem. So how to solve vector problems. So let me grab it here. So in this problem, a lady launches a boat from one shore of a straight river. Okay, so I think the river is flowing. Okay, so we can take the river to be going in this direction, okay? And so she launches a boat from one shore of a straight river and wants to land at the point directly on the opposite shore. So she starts here, and she wants to end here, point directly opposite. If the speed of the boat relative to the water is 10 miles per hour, okay, and the river is flowing east at 5 miles per hour, okay, so here's the east direction, okay, the problem gave you a little compass, okay, a cardinal direction, so the river is flowing in this direction at 5 miles per hour. In what direction should she head the boat in order to arrive at the desired landing point? Okay, so W represents the vector connecting the two shore lines. Okay, the shortest distance between the launch point and the target point. So that's W. All right, and notice we don't have any information about how far apart the two banks are. All right, so what we do is the procedure is we set up a coordinate system as shown here in the illustration in this particular picture. Okay, so we have the y-axis pointing north and the x-axis pointing east. Okay, so here's the x-axis. It's a little bit grayed out there. Okay, and then u is the velocity of the river and b is the velocity of the boat. Now, the velocity of the boat, the magnitude of the velocity of the boat is 10. So we said she's going 10 miles per hour, but we don't know what direction she's going in. So that just means that if we just know the magnitude of the vector is just 10, and u is the velocity of the river, so we would take u to be, okay, so the way you would set it up is, since the river is flowing due east, all right, so its velocity vector, okay, in other words, a magnitude times a direction would be 5I, because I, remember what I is equal to the unit vector 1, 0. Okay, and 1, 0 represents the easterly direction. Okay, so let's talk about this. So the river heads east, so that would be 1, 0. Now if the river were heading west, okay, then I would equal to -1, 0. That would be a westerly direction. Okay, and since the lady is heading north, okay, if she were to head due north, that is, but she's not heading due north at the outset, then she would be heading due north would be represented as the unit vector 0, 1. And if she were heading due south, okay, then the unit vector for due south would be 0, -1. All right, so just to keep things in perspective. All right, now anyway, so we understand now that the velocity vector for the river current is 5I. Okay, now this lady tacks at a particular angle theta. So if she's going to want to land at the point opposite, then she would probably want to tack against the flow of the river, because the flow of the river is going to push the boat back toward the this perpendicular toward the y-axis, right? So she'll have to head out to the left of her destination point, because the force of the river will push the boat back toward the east. So you head west to compensate for the force of the river pushing on the boat. Okay, the force of the river current pushing on the boat. So that means her vector, her velocity vector, would be represented by a magnitude times the cosine of theta. So this would be this quantity right here would be the horizontal component of her velocity vector, and then 10 sine theta would be the vertical component of her velocity vector. Okay. Now by vertical component, I shouldn't really say vertical component. This would represent the northerly component of her velocity vector, and then this would represent the westerly component of her velocity vector. As you can see in the, I shouldn't say vertical, but it would be westerly component. See, in the east-west direction you go horizontal, and in the north-south direction you go vertical, in a sense, okay? So this would be the westerly component of her velocity, and this would be the northerly component of her velocity. And so the result, okay, now, so the resulting vector, okay, the resulting vector would be, yeah, the net effect is that she would want to be heading due north, okay? She would want to be heading due north from her point. So that means that the resulting vector, we would want some sort of, we would want basically the horizontal, the east-west components. Okay, this is east. We would want the east-west components of the sum of the two vectors to cancel, because if the east-west components of the sum of the two vectors cancel, then the only thing left would be the northerly component of the vector. Okay, so that would be the strategy, to cancel out the east-west components of the two vectors, so that they sum to 0, and then if the east-west components of the sum of the two vectors sums to 0, then the only thing left would be the vector, the northerly direction of the velocity vector. Okay, all right. So that's how you would think about it. Now, so summing the two vectors, we'll have 5I plus 10 cosine theta I, and then the northerly component vector. So you just sum the components according to the rules for summing vectors, and that requires that 5 plus 10 cosine theta must equal to 0. Now if we look at, okay, and so solving for cosine theta is equal to -1/2. So theta must equal to 120 degrees, which is consistent with the drawing. Okay, so she must have 120 degrees with respect to the positive x-axis to get there. And so what would that be in terms of bearing? In terms of bearing, that would be what? Okay, well, this would be 60 degrees here, right? And in terms, and this would be 30 degrees here, right? Okay. And so her bearing then would be north 30, west. Okay, so if you recall the lecture notes from chapter 3, so that's our bearing. Okay, all right. Might be a web assigned question to ask you about a bearing for the resultant vector. So this is, yes, that's how you would solve that. So now the next problem is a little bit of a challenge problem. So let's step through that. And this would be the last problem of section 5.5, I believe. Let me check if there are any more after this. Yeah. Okay, so let's do that one. All right, so in this illustration, we have a construction site, kind of like downtown Anchorage now these days, right? So anyway, the cranes in the figure are lifting an object that weighs 18,278 pounds. And you want to find the tensions in the two ropes, okay? So basically the force in the two ropes. And they show you the angles of elevation with the horizontal of the two ropes, 22.3 degrees here and 41.5 degrees here. So you basically, you want to find the force that these two ropes are tugging on this weight with. Okay. All right. So now to do that, what we have to do is we have to set up our coordinate system, and so we'll let the weight, the tie point where the two ropes are tied, we'll let that be our XY plane. All right. So let this be our XY plane, like so. Okay. All right. So far so good. And so what we do is we formulate an expression for vector T1. Okay. So T1. Okay. That would equal to, okay, well, now remember in vector form, you have a horizontal component and a vertical component. So in this case, we have a true horizontal component. So that would be, well, in the x direction, the horizontal component for T1, since it's to the left of the origin, it would have to be the magnitude. Now we're talking about horizontal component. The magnitude of, sorry, of what we need to find, the magnitude of T1, times the cosine of 22.3 degrees. Okay, so, and then we would use the unit vector I. So that would be the horizontal component of the tension in T1, the force in T1. And now the vertical component, well, since the vertical component of T1 goes in the positive y direction, that would just be the magnitude of T1 times the sine of 22.3 degrees. And that would be in the, you can also write J with a hat above it. Okay, so that's T1. Now for T2, okay, so let's talk about the formulation for vector T2. So that would equal to, well, T2, the horizontal component of T2 goes in the positive x direction, so that would be the magnitude of T2 times the cosine of, what, 41.5 degrees. Okay, plus, and the vertical component of T2 is in the positive y direction, so that would be the magnitude of T2, I should put the arrows over, times the sine of 41.5 degrees. All right, so we have our vector specified. Now, so the thing is we have this weight pulling down. Gravity is trying to pull this weight down, and then the ropes are trying to pull it back up. So if the system is in equilibrium, then the vertical forces on the weight would, the sum of the vertical forces on the weight must equal to 0. Okay? If there's no motion in the system, then if there's no vertical motion in the system, then the sum of the vertical forces must equal to 0 because, yeah, force, there's no motion. So since we'll assume that there's no motion, vertical motion, then we would have, or horizontal motion for that matter, if the system were completely at rest, the weight is not moving either vertically nor horizontally, then we would have that the sum of the vectors, T1 plus T2, must counter the gravitational pull on the weight. And the weight is 18,278 pounds straight down, okay? Like so. All right, so so that means that the sum of the horizontal components must equal to 0. So since the weight is not translating either to the left nor to the right, we would have T1, the magnitude of T1, times the cosine of 22.3 degrees. That must equal to the magnitude of T2 times the cosine of 41.5 degrees. Right? no horizontal translation of the weight. So that means we can solve for the magnitude of T2 in terms of T1. So the magnitude of T2 is equal to the magnitude of T1 times cosine of 22.3 degrees divided by the cosine of 41.5 degrees. Okay. Now, for the vertical component forces, we require that let's see, use a different color here, that the vertical component exerted by T1, rope T1, okay, so the vertical component from rope T1 is T1 times the sine of 22.3 plus the vertical component asserted by T2, which is T2 times the sine of 41.5. That has to counter the opposite weight, the weight pulling down. Okay, and so that must equal to 18,278. All right, so the forces all cancel. So, so now what we can do is we can replace T2 by its expression in T1. It's equivalent in T1. So in doing so, we formulate the equation. So we'll plug in this value right in here. All right, and so when we do that, we get T1 times the sine of 22.3 plus T1 times the cosine of 22.3 times the sine of 41.5 divided by the cosine of 41.5. Okay, and that must equal to 18,278 pounds. All right, and so so now we just have an algebraic equation, so we can factor out the T1. So we can solve for T1 here. And I won't go through all of it, but the book goes through a relatively lengthy algebraic solution of this. So I'll just go ahead and show you how to solve it algebraically. As you can probably recognize early on that this is nothing more than an algebraic solution. So let me just, for the sake of time, show you the progression of the solution as it's depicted in the notes. So now we're solving for T1. So we pick it up right here. So if we were to multiply, let's see. All right, so pick it up right here. Multiply both sides of this equation by cosine of 41.5 degrees. There should be a T1 right here, got truncated. And then, so right here, if you recognize this expression right here, this would be the sine of a sum of two angles, right? So this would be T1 times the sine of the sum of the two angles is equal to this quantity right here. And so T1 is equal to 18,278 times the cosine of 41.5 degrees divided by sine of 63.8. You should recognize that this is a trig identity. And so solving using your calculator in degree mode, you'll see that T1 is equal to 15,257 pounds magnitude. And so then you calculate T2 based on this ratio right here. Okay, so you plug in the value for the magnitude T1 and you'll get to T2. Let's see. Oh wait, T1 in the first case, T1 is equal to T2. So we found T1. I'm not sure what they're doing here. T1. Oh, they're going back to the first equation again. Let's see, what equation are they using here? Oh, they're using this one? T1. I have no idea what they're doing. Oh, let's see. Cosine. What on earth is this? This doesn't look right. This looks a little bit inefficient here. I'm trying to interpret this information. Cosine of 41.5. Let me check that. I got it mixed up here. T1 is equal to that. Solving for T1. 1 second here. I'm not sure if it's worth to go through this. No, I would not do the problem this way. This is totally not correct in the solution. So let me see if I can fix it here. So the T1 is correct. And then we have T2. Okay, so T1 is equal to that. So T2 times. Okay, well this really isn't the ideal solution. What I would do, since we have now a value of T1 is 15,257, I would just go ahead and plug it into this equation to get the magnitude of T2. And so to solve for, and then you would get the magnitude of T2, which is what we want. All right, so it turns out that T2 the magnitude of T2, so if you were just to use this equation, the magnitude of T2 found more simply would be, yeah, that's not the best way. The magnitude of T2 when using this equation would be 18,847 pounds. Okay. And so now that you know T1 and T2, you can just plug those quantities in to the here and here, and then you'll have T2, and then you can do the same for T1. So they made the solution of this problem a little bit unnecessarily complicated. But that's how you can, that's a simpler way of dealing with it. All right, so that's all I want to say about section 5.5. The next topic, section 5.6, the final topic of chapter 5, we'll talk about more applications of vectors. So we'll end the lecture right here.